So today we're going to be looking at complex zeros and the fundamental theorem of algebra. This is coming straight from section 2.5 of your textbook. I'm going to be pulling definitions and examples from that section. So if you are looking for more explanation or more examples, that's going to be the place to look. The first theorem that we're looking at is the fundamental theorem of algebra. So a polynomial of degree n has n complex zeros, real and non-real. Some of these zeros may be repeated. So in simpler terms, this is exactly what we've talked about earlier in the week. For example, if you have a fourth degree polynomial, that polynomial has 4 zeros or 4 roots. Some of them may be repeated, so like if it has a root at 1 but with a multiplicity of 2, that counts for 2 roots even though it's the root is only at 1. They can be real and non-real, irrational, and so on. So if you had a degree 6 polynomial, you would have 6 roots. All right, the second theorem is the linear factorization theorem. So if f of x is a polynomial of degree n greater than 0, then f of x has precisely n linear factors. And it's written like this, where a is the leading coefficient of f of x, and z sub 1, z sub 2, and so on are the complex roots of f of x. The z sub 1 are not necessarily distinct numbers, some may be repeated. So this is kind of the same thing as what we were saying before, except that once we find the roots, we can write them as factors, and when we multiply them together, that's what we're going to get. It should equal f of x. One thing that the book does a good job of pointing out is that the fundamental theorem of algebra and the linear factorization theorem are existence theorems. So they tell us about the existence of zeros and linear factors, but not necessarily how to find them. Okay, so for our first example, this is example 2 in the book, and it says to write a polynomial function of minimum degree in standard form with real coefficients whose zeros include -3, 4, and 2 minus I. All right, so the first thing you should notice is because there is this complex root, there has to be another complex root, its conjugate. So complex roots and irrational roots come in pairs. So this 2 minus I means that there's also another root 2 plus I. So you're never going to have a complex root be a root without its conjugate as well. So that means we have 4 roots. So we're going to end up with a fourth degree polynomial. All right, so when we write this as a linear factorization, remember we say x minus the root. So for this, we have f of x equals, and it's going to be x minus -3, which we know is going to turn to +3, but we'll leave it like this for now. And then it'll be x minus 4. And then here it can get a little tricky if we're not careful. So this is going to be x, and then we're going to subtract this whole entire root. So we need to put another set of parentheses and make this 2 minus I. And then same thing here, this is going to be x minus, and we're going to subtract the whole root, so 2 plus I. Okay, before we do anything else, we should simplify what's going on in each of these individual parentheses. So, still talking about f of x, and then we have x plus 3, x minus 4. This is going to be x minus 2, and then when we distribute this negative, it'll be plus I. And then this will be x minus 2, and then minus I. All right. So at this point, I think what I would do is go ahead and it's not really FOIL because we're not multiplying binomials, but distribute out, multiply out these two factors. And let's go ahead and clean that up. So you can also go ahead and multiply these two together just because we're going to end up multiplying it all out eventually. So we can go ahead and do that. That would be x squared minus 4x plus 3x minus 12. And then over here, it's 3 terms each. So we're going to have x squared minus 2x minus x times I minus 2x plus 4. This is going to be negative times the negative, so a plus 2i. Then we're going to have I times x, or plus xi, minus 2i, and then minus I squared. Okay, so we've got 9 terms because it's a 3 by 3, and it looks really complicated, but if we've multiplied it out right, then in this section we should always be able to cross quite a bit out. So in the first part, let's go ahead and simplify this. So it would be x squared, and then that's going to be minus x minus 12. So just simplifying, combining those like terms. And then over here, we have a plus 2i, a minus 2i, a positive xi, a negative xi, so that leaves us with x squared minus 2x plus 4 and minus I squared. So I squared, we remember from dealing with complex numbers, is actually equal to -1. So this is going to be x squared, and then these combine to be minus 4x, and then this is going to be 4, and then minus -1, so plus 1, so plus 5. All right. And so then we just have to distribute one more time, and we'll have our 4th degree polynomial in standard form. So at this point, we multiply these two. That'd be x to the 4th minus 4x cubed plus 5x squared minus x cubed plus 4x squared minus 5x minus 12x squared plus 48x, and then minus 60. And then of course we want to combine like terms. So there's no like term with x to the 4th, but we have a negative 4x cubed and a negative 1x cubed. So that's going to be minus 5x cubed. Then we have a 5x squared, a negative 12x squared. So that, well, and we also have a 4x squared. So together that will make a negative 3x squared. We have a 48x and a negative 5x, so that added together makes 43x, And then the 60 does not have a like term, so that's just going to be minus 60, or the negative 60 doesn't have a like term, so it's just minus 60. So this is our final answer. It's a fourth degree polynomial in standard form, and it has zeros at -3, 4, 2 minus I, and then 2 plus I.